Thank you. Then this is a joint work with Christophe Bess and Ingrid Joly in Lille. Ingrid is somewhere in the audience. And this work has been continued during this summer, during the last session of the SEMRAX by Frédéric Charles and Nicolas Vauchelet. And as I will explain to you in a minute, the origin of this work comes from a collaboration with Thales from some problem arising in spacecraft engineering. And this is a collaboration with Jean-Paul Dudon. And this work takes place in the context of the PhD thesis of Serge Borgol. Okay, then this is to explain the origin of the problem. We consider this kind of satellite, of spacecraft, and it evolves in the plasma, then it interacts with ions and electrons. And this interaction produces electrical charging of the spacecraft because the surfaces of the spacecraft are made of conductor or dielectric surfaces. And the problem is not the charging, but the fact that some differences of potential appear. And due to the differences of potential, some electrical arcing can be produced. And in particular, the solar array are very sensible to this phenomena. And in particular, you can burn some zone of the solar array, and then the satellite is lost. Then this is a big issue for a company like Thales. And then they want to understand and to prevent this kind of phenomena. Then the basic model are made of Vlasov-Poisson, Vlasov-Maxwell-Boltzmann equation. But you have plenty of parameters in the equation. And the value of the parameters depends on the plasma that you consider. And in particular, it depends on the orbit where the satellite is flying. And the value of the parameter changes if you are in the geostationary orbit, or in a low orbit, or in the polar orbit. And then in some circumstances, it makes sense to consider, instead of a kinetic modeling, to start with a fluid model, at least to understand very quickly what happens. Okay. Then the first motivation comes from this question. You want to replace a kinetic model for this complicated question by a fluid model. But the question is now, okay, you have replaced your kinetic equation by the Euler system. But what is the boundary condition to be used for the fluid equation? Okay. Just to tell you that for the problem of the spacecraft engineering, the part which is interesting is the boundary condition for the electric potential. This is something which is not standard, which is very complicated. And I will completely get rid of this difficulty, since actually the question I consider is quite general and can be considered also for gas dynamics. Okay, then this is just to explain the motivation, but now I switch to something simpler. I completely get rid of the coupling with electric phenomena, and I just consider gas dynamics. Okay, then I will spend a lot of time explaining things that almost all of you know by heart. And I start by recalling the problem of hydrodynamic limits. You start from the BGK equation, which is this one. Of course, you can replace BGK by Boltzmann, but BGK is simpler for the talk. Then here you have the transport part of the equation, dTF plus BdXF equals something, which tells you that you have some collision effect between the particles. And the effect of the collisions is to relax to F, the distribution of the particles, to a Maxwellian. And M of F is defined in this way. This is a Maxwellian with quantity rho, u, and theta, which are defined as moment of capital F. Okay. Okay. The problem is nonlinear since this quantity is nonlinear. Just to set up a few notation, I use rho, g, and e defined in this way as to be the moment of F, with p is the vector 1, v, and b squared over 2. And you can define equivalently rho, u, and theta. Then you have a transformation between rho, u, and theta, and rho, j, and e. Okay? Then you keep this transformation in mind. Then as the mean free path tau goes to 0, the leading effect is the collision. Then F relaxes to the Maxwellian. This is exactly what is explained here. And now the macroscopic quantity, rho, u, and theta, that depend on t and x, the time and position, will satisfy the Euler system. Okay? Just let me remind why. This is because the collision operator satisfies some conservation property. If you multiply the equation by p times Maxwellian minus f you integrate with respect to v, you obtain 0. This is due to the very definition of the Maxwellian. And if you multiply the equation by p, you get this family of conservation law. And of course, the system is not closed because here, in the flux term, you cannot express this quantity by lower order moment. In particular, if you think of the energy, the last line of this equation is the moment of order 3, and in general, it cannot be expressed by means of the moment of order 0, 1, and 2. Okay? But now you go back to the relaxation effect. As tau goes to 0, f looks like the Maxwellian. And now if you replace f by this ansatz, the leading term in the ansatz, by the Maxwellian, you are able to close the equation since you have only to compute moment of the Maxwellian, which is a calculus exercise, and you get the Euler system. Okay? Just to warn you that here in this equation you have factor 3, which is not the usual one. This is because I'm working in dimension 1. The velocity variable belongs to R and not to R3, and then it changes the value of this coefficient. Okay? Usually in dimension 3 this is 5 instead of 3. Okay, and I warn you again that you have the change of unknown. Either you work with the conserved quantity, which is this fancy U, defined this way, or with the physical quantity, which are the density, the velocity, and the temperature. Okay? And sometimes it's better to think of rho u and theta, and sometimes it's better to work with fancy U. Okay, the problem I want to consider now is the fact, okay, I consider the equation, I let tau goes to 0, I understand that f relaxes to a Maxwellian, I obtain the equation in the interior. But now this equation is set on a bounded domain, minus omega plus omega. You have to consider the boundary condition for both equations. And the point comes from the fact that the kinetic equation, you have a certain boundary condition, and maybe this boundary condition is not compatible with the thermodynamical equilibrium. It can be different from the Maxwellian. And therefore, you have a boundary layer, which happens due to this incompatibility between the boundary condition at the kinetic level and the leading term in the expansion of the kinetic equation, of the kinetic solution. And now I can address two questions. Question one is, what is the boundary condition for the Euler equation, for the hydrodynamic fields? I remind you, you start from a kinetic equation with a given boundary data, and now the question is, are you able to write the boundary condition for rho, u, and theta? This is question number one. And question number two is, okay, imagine that you're able to answer positively to question one. You have a certain formula, but what do you do numerically? Are you able to use this formula in your numerical code? In particular, what do you write on the boundary flux or your favorite finite volume method? Okay. And certainly the formula that you obtain in answering question one is not tractable for numerics. Then you have to do something, another approximation. And then really my talk is in this numerical perspective is how to define numerical fluxes which are consistent in a certain sense to the hydrodynamic limit. Then, of course, the problem is, has been investigated a lot, and I just give a few references. I apologize since I skip a lot of key results, but just a few of them. As we will see in a while, question one leads to the analysis of half space problem. Okay, it means equation like that. You should consider this equation, which is a stationary Boltzmann equation, or BGK, for the non-negative V in R, and you fix a boundary condition at z equals 0 for incoming velocity. Then you should consider a problem like that. And actually, I will spend a lot of time during this talk going back to a paper by Coron, Goltz, and Sulem about the linearized Boltzmann equation of BGK. That's the same. But quite recently, the analysis of the half space problem has been revisited. In particular, there are a series of very interesting work by Ukai, Young, and Yu. Okay, second comment is here in this talk I consider the problem of the boundary value problem, but actually it is maybe more relevant to consider the problem of matching kinetic to fluid equation. What I want to say, actually it is maybe more interesting to consider the following situation where you have the boundary here, you have the wall, and here you have a domain where you solve a kinetic equation. Here a certain boundary, and now you consider a fluid equation. And here what you have is your Q of F. If you wish, you can obtain this description by inserting the mean free path only in this domain, in the right domain. And now the question is, looking at this limit, what is the matching condition between the Euler equation in this domain and the boundary condition for the kinetic equation? Okay, then this problem has been considered as well. And I refer to a recent paper by Alexis Vasseur for the scalar case, but you have complete references on the question. And the question of the scalar case has been completely solved by Alexis. I should mention also that the numerical investigation of the phenomena of the boundary layers has been investigated by the team of Sonnet and Aoki, and you have plenty of very nice and very deep results about that, showing many unexpected results. And about question 2, about the numerical purposes, I should mention the work of Goltz, Jean, and Livermore about diffusion limit. Question is a little bit different. You start from, let's say, the radiative transfer equation, and what you obtain instead of the earlier equation, you obtain the heat equation. And the question is the same, is now, knowing the boundary condition at the kinetic level, what is the boundary condition for the heat equation? Okay? Then the analysis is a little bit easier, and you can also derive what you should do at the numerical level. This is explained in this paper. And going back to the hyperbolic limit, I mentioned also the numerical solution proposed by Stéphane de Lacherie. I will go back to that in a minute, which is something which is quite cheap and which works well, actually. Okay. Let me enter more into the details. One has to prescribe the incoming fields. Then it is quite easy to understand what's going on for the kinetic equation. Imagine that the kinetic equation, your domain is starting here. You have a positive velocity, then you have to prescribe what enters into the domain. If the velocity is going outside, then the particle goes out, and that's it. There is nothing to prescribe. You have just to prescribe what is coming into the domain. Then this is exactly what is written here. You prescribe at x equal minus omega the distribution of particles with positive velocity, and at x equal plus omega, you prescribe the particles which are incoming. That means with negative velocity. Okay. This is very clear for the kinetic level. But now for the Euler system, it becomes really a mess. This is a nightmare, since the number of quantity you have to prescribe depends on the flow itself. Okay? Then you have three quantities, rho, u, and theta, but you do not know a priori what you have to prescribe. Just for rho, just for u, just for theta, or for the free overalls. We will see that in a while. Okay, then the nature of the boundary condition and the number of boundary conditions depends on the flow. And just to explain the question number 2, you think of a finite volume discretization, then your hydrodynamic unknown is discretized in this way. And now you have to use a definition of the flux here between the cell j and j plus 1. Think, for instance, to 2-point fluxes. In the numerical simulation, we use a good enough fluxes, but you can think of upwind if you wish. And the question now is, for the boundary cell, how do you prescribe the boundary flux? Okay, and of course, it will certainly depend on the kinetic data. Okay, taking into account the boundary layer. This is the question I want to consider. Okay. Then a key point in this question is the notion of entropy, as it it appears already clear in many talks. Then the entropy is dissipated by the BGK equation. It means that if you consider f logarithm of f, in other words, you multiply your collision by logarithm of f, then you get something which is dissipated because this quantity has a sign. Okay. This is again a simple computation that uses the property of the Maxwellian m of f. Then here in this talk we do not care of the specific form of the dissipation, but you care of the dissipated quantity. The good news is that it provides natural entropy for the Euler system. If you go back to the talk of Vasseur yesterday, the quantity eta of u plays a crucial role in the analysis, but here you know for free this kind of quantity, which is convex quantity depending on u, just by replacing f here, capital F, by the Maxwellian. Then this quantity is a strictly convex function of u, and as soon as the solution of the Euler equation is smooth, is satisfied this equality. Okay. And the Q of u, of course, is exactly the entropy flux evaluated for capital F equals m of u. It's exactly the same. Okay. Then you have an entropy, and actually it's better to work with the relative entropy, which is defined in this way. It makes the difference a way to evaluate how far m of u is from another reference state m of u star, since this quantity is non-negative. Okay, it is non-negative and its derivative with respect to u at u star vanishes. Okay, I will use this property later on. And this is a good tool to understand what we have to prescribe for the hydrodynamic fields. Okay, then let me switch to a simpler problem. I will consider now a linearized equation instead of the full BGK. I linearize the equation. Then I expand capital F, the solution of the kinetic equation in that way, around a given absolute Maxwellian. Rho is a given constant, positive, theta star also, and u star is a given real number. Then you assume that capital F expands in this way, where delta is small enough, and you keep only the leading term in the equation, and you get the linearized BGK equation, which is quite simpler, since the m of f now, this is an infinitesimal Maxwellian. It defines actually nothing but the projection of small f to 1 v and b squared, the set of invariant quantity for the kinetic equation. Okay. Then now I consider the fluctuation, rho tilde, u tilde, and theta tilde, and it parameterizes the infinitesimal Maxwellian. Okay. They are defined by means of small f in this way. Okay. This is just the projection of f on the set spanned by 1b and b squared. Then, as before, you can let tau go to 0 in this equation, and you understand, at least formally, that f looks like the infinitesimal Maxwellian, and the macroscopic quantity u tilde satisfies the linearized Euler equation. Of course, it coincides with the results you obtain if you linearize the Euler system around the constant state rho star, u star, and theta star. Okay. Then the linearized Euler system reads in this way, with this matrix A star. And if you look at the eigenvalues of A star, you obtain u star, and u star plus or minus the Sun speed, which is here in this context square root of 3 theta star. Okay. Then what you can guess at this level is you can look at the sign of the eigenvalues, and it gives you how many boundary conditions you will need. If you have the three eigenvalues are positive, then at x equals 0, everything is incoming, and you have to prescribe three quantities. This is what we will see right now. Then let me use the entropy to understand how it works. Then you can go back to the conserved quantity. As I tell you, you have this transformation between rho u and theta and rho j and e, the conserved quantity in the Euler system. But now you linearize around the state u star, and you get a linear transformation between the fluctuation of the conserved quantity and the fluctuation of rho u and theta. Okay, you have a certain matrix P star. I don't want to write it now, but you have a linear transformation. And of course, you can express the linearized Euler equation by means of the conserved quantity. You obtain the system where this matrix is related to the previous one by using the change of coordinate with p star. Now you use the entropy. You look at the evolution of the relative entropy between u and the reference state u star. You get this equation. You expand it, saying that you are considering a small fluctuation around u star, and you get this relation. Of course, you obtain exactly the same by multiplying this equation by S star, which is the Jacobian matrix of the relative entropy evaluated at the reference state. And of course, since the relative entropy is a convex function of u, this quantity, this matrix, is symmetric positively finite. Okay? And the second point is the fact that this matrix here, the flux matrix for the entropy, is defined this way, and this is also a symmetric matrix. Why it is important? It is important because it gives you a way to obtain energy estimates.
Is the first derivative not the second one, right? In the previous slide.
Which one?
The definition of S star is d eta. Otherwise, I don't know.
No, this is the second derivative. This is the Jacobian of the matrix. The first derivative vanishes.
Ish.
This is the Hessian.
Ish. Okay.
The Hessian. I said Jacobian?
Then you would get the
Oh,
second
sorry.
one.
The Hessian. The second derivative, sorry. Is it okay now? No?
Then you would get the second time derivative. If you take just the chain rule.
No, I mean it's the symmetrizer. I think it's the
Okay.
Okay, then it gives you a natural way to symmetrize the system, and you get entropy or energy estimate from that. You multiply the equation by u tilde, and you use the fact that this matrix is symmetric, and you obtain this relation. You integrate with respect to time, and now you separate terms to keep only terms with the good sign. What I mean in this way is that you look at the boundary term now. Here I get the positive part of this quantity. Here the quantity which has a good sign. The negative part is positive, and there's a plus in front. And on the right hand side I have the initial data and the boundary term with the bad sign. And then what you have to prescribe is precisely the red quantities. If you prescribe these quantities, you get from this entropy estimate at least the uniqueness for the linearized problem. This is something which is quite standard actually. Then let me go back to the kinetic equation. You look now at the entropy dissipation at the linearized level. Then the quantity to be considered is the linearized entropy, which is defined in this way. And the entropy flux, which is the moment of F squared times m star. You evaluate this quantity at the Maxwellian, infinitesimal Maxwellian associated to u tilde, and it defines the quadratic quantity with respect to u tilde, okay, with a certain matrix sigma star. And now you can relate all these matrices, all these quadratic form, to define n plus minus the number of positive or negative eigenvalues of the flux matrix in the Euler system. Then the signature of this quadratic form is n plus n minus. Okay, then the entropy flux gives you exactly the signature associated to the entropy flux is exactly given by the eigenvalues of A. This matrix can be expressed in this way. Of course, this is only the change of coordinate between the u and the fancy u. And now you can split the kernel of the collision operator into three sets, three vectorial spaces, where this quadratic form is positively finite, negatively finite, or the radical of the quadratic form. And the dimension of each of these sets is given by n plus minus, or the dimension of the radical. Okay, actually I will skip the case where you have something in this set. Okay, let me make a summary now of what we did. If you look at the left side of the equation, if u star is larger than the sound speed, you have three incoming characteristics, then you have to prescribe three quantities. If the sound speed is related to u star in this way, you have two incoming characteristics, you have to prescribe two fields. And now you have one incoming characteristics, one quantity to be prescribed. And if you are in this situation, everything goes out, and then you have nothing to prescribe. Okay? Then you understand why in the nonlinear situation it is really complicated, since of course you can do exactly the same by writing the Euler system in the non-conservative form, and you do exactly the same reasoning now on the matrix A of U. But of course now the number of incoming characteristics depends on U, while here we are considering a given state U star. Okay. And then there is an adapted basis to do the computation. Let me explain it now. As I said, the kernel of the collision operator is given by the infinitesimal Maxwellian, parameterized by rho tilde, U tilde, and theta tilde. And you consider the entropy flux as a linearized level defined in this way, and you get this quadratic form. Now you introduce this basis of the kernel of the collision operator, and the good news is that this basis is very well adapted because all the functions are orthogonal, and the entropy flux of this quantity gives you exactly something which is related to the characteristic, again to the eigenvalues. Here this is rho star, U star, and here you have the difference with the Soon speed. And this is very well adapted to do computation easily. And this is exactly the sense of the last sentence. You have exactly this decomposition of this set according to this basis, where you have as many functions as the dimension of the gain space. Okay. Okay. Now let me go back to the half space problem. How it occurs in the analysis. You start from the linearized BJK equation with given incoming data. Then in the left-hand side, you prescribe the incoming velocity, V positive. On the right-hand side, this is a plus here, sorry. You prescribe a negative velocity. And to understand what's going on, you expand the solution of the kinetic equation this way. Here you have the leading term, which takes into account the relaxation effect due to the collision. And you add some correction which zooms on the boundary. Okay, and this quantity are expected to vanish very fast as tau goes to 0. And then you insert this and that in the equation. You keep only the leading term, and what you get is exactly as I said before, this equation, which is set for Z non-negative and V in R, with an incoming boundary data. And the incoming boundary data depends on the incoming data for the kinetic equation minus the first term in the expansion. And this is the quantity that you are searching for. You want to identify the boundary condition of that guy. Okay, you don't know exactly what it is. Okay, and then you look at the analysis by Courant, Goltz, and Sulev. The result is the following. You define a certain subset of the kernel of the collision operator, where the quadratic form defined by the entropy dissipation is non-negative. This subspace should be maximal in a certain sense. Then for a given incoming data with a certain regularity, you can solve the half space problem, and there exists a unique state, which is the asymptotic state, which belongs to V plus, solution of the half space problem, and M infinity is exactly the state of the distribution function as Z goes to plus infinity, since you have this estimate. Okay, that's exactly the result of Courant, Goltz, and Sulev. Then another way to think of the result is to define a linear mapping which associates to the data of the half space problem the state at infinity, M infinity. Okay? And then the boundary layer correction is expected to vanish far from the boundary. If you go back to this relation, what you expect is that this term has no influence when you are far away from the boundary. Then as tau goes to 0, it should be 0. Then it means here as Z goes to plus infinity. And then if you expect that, it means that M infinity should be 0. It means that you have this relation. And that gives you the boundary condition you are searching for. The boundary condition for the hydrodynamic field is to say that this operator, C star, applied to m of u tilde is exactly c star of phi. Okay. Another way to think about the results is the following. I will use this point of view to define the numerical flux. Is to think as follows. You split your hydrodynamic unknown into two parts. A part which belongs to lambda plus, okay, and a part which belongs to lambda minus. The part with m minus corresponds to characteristics which are outgoing. This is the part which is known, actually, given by the fluid. And what we are really searching for is a part which is incoming into the domain. This is a quantity that has to be determined. In other words, m plus is the asymptotic state that corresponds to the solution of the half space problem with given data phi minus m minus, the outgoing part. Is that clear? Then in particular, when n plus equals 0, then you have no incoming characteristics. Lambda plus is reduced to 0. Then you have nothing to prescribe, and indeed m plus is 0. Okay, so you have no choice. And with this analysis, you understand that the incoming characteristics is defined as a functional of the kinetic boundary phi and of the outgoing characteristics. Okay? And of course, it simplifies if you are in a scalar case, since you have only one characteristics and there is nothing else to say. You have just incoming or exiting. But you have no this kind of mixed state. Okay, now you define the boundary condition by using this operator C star. But how can you use this relation in a numerical perspective? How could you define the numerical fluxes? Okay, then I write my finite volume scheme in this way. And the point is to define the fluxes for the first boundary, for the first cell, sorry. And the idea is to write these fluxes as the integral of a certain infinitesimal Maxwellian. Okay, as the flux of, sorry, something is missing. There is a p which is missing. This is 1 v and v square times m boundary m star dv. How do we define this quantity? First, I introduce this infinitesimal Maxwellian, which is associated to the unknown, the numerical unknown, in the first cell of the computational domain. Okay. Then I know this quantity, and I associate this infinitesimal Maxwellian. Now you are projected on the outgoing subset. In this way, it defines the alpha minus. Okay, I know the part of the solution which is going outside, and now I define m plus by solving the half space problem with incoming data, the kinetic quantity, the phi, minus the quantity I have determined now. Okay, then of course I have to explain something about from the half space problem. Okay, now I define my infinitesimal Maxwellian of the boundary as to be m minus plus m plus. But of course here I'm cheating, since solving the half space problem is certainly as difficult as solving the kinetic equation with a small parameter. You have to solve the kinetic equation on the infinite domain with a given data, and you are searching for the state at infinity. I don't know any numerical scheme able to do that. Okay, then this is where I need another approximation step. And the idea is to use the conservation laws associated to the equation. Then if you look at the half space problem, you remark that you have conservation laws. Maybe I should rewrite the equation here. The half space problem is written in this way, and then you use the conservation property of the collision operator, so that you multiply by p, you integrate, you obtain 0, and you obtain exactly this equation. Then you integrate with respect to z, and now you remind that your asymptotic state is supposed to vanish at infinity. Then the relation that you get from that is the fact that you have this relation. Then here, this quantity splits into the quantity that you know, which is the boundary data for the kinetic equation, the part of the flow which is going outside, and now the quantity that you seek. The problem is that now the outgoing part of the distribution function is completely unknown. You don't know what is that guy. And then there is a device which is known as the Maxwell approximation, and some people know this approximation as the Marshak approximation in the field of radiative transfer. It's simply to say that the outgoing distribution coincides with the asymptotic state. And here this is quite simple. So the asymptotic state is 0. Then I replace this guy by 0. And then I obtain this equation to define M+. Okay? Of course, here there is an approximation. Okay, let me remind what we want. We want to define M+ with quantity ρ plus, U plus, and theta plus. They are your rank knowns. It should belong to lambda plus, a certain subset. And you want to satisfy this set of equations. And of course, you have a problem if you have only, let's say, 2 incoming characteristics. Then you have 3 relations and only 2 unknowns, since saying that this guy belongs to lambda plus imposes a relation between the coefficients ρ plus, U plus, and theta plus. Okay? Then you have too much relation, and what you do is to eliminate some of them. And I know at least 2 strategies. The first one is just to say, okay, let me pick as many relations as I need. This kind of strategy appears in the paper by Goltz and Clar, and also in the paper by Arnold and Gehring. But I should say that I do not really understand how to pick the relation that you use. And for this reason, what we choose is to use instead a least square approximation. Then we do the best that you can do. It means that you minimize among the M+ in this set the quantity obtained by the Maxwell approximation. Okay? And then now I define the numerical flux in this way. I know the M-, I know the M+. I am able to compute this integral. Again, the P is missing, sorry. And it corresponds exactly to upwind fluxes if you write the systems in diagonalized form. Okay? Then it means that if something is going outside, you prescribe nothing. If something is coming inside, then you use the definition of the M+. Then some result for the linear equation given here. You compare the hydrodynamic simulation to the kinetic simulation. Here I think that the incoming data is 0, and the comparison is quite good. Well, actually, I should say that we started with the nonlinear problem. Then I understand much better the simulation for the nonlinear situation than for the linear case, since the linear case has been investigated during the summer, and I should look more carefully at the simulation. Then I show you something which works quite well. Okay, let me now show you that we can extend this kind of strategy to deal with nonlinear problems. And the first idea is to say, okay, let me consider a situation where the initial data for the kinetic equation is close to an absolute Maxwellian, and therefore the initial data for the Euler system is close to a constant state. Okay? Then I can expect that I remain quite close to the constant state, and then the fluctuations are approximately solution of the linearized Euler system. Okay? Then I can repeat what I did, and I define now the numerical flux in this way. Now the P is appearing. With still the same definition for M of the boundary, and M- and M+. Okay? Defined with respect to this absolute Maxwellian, which is defined by my initial state. Okay? Then it doesn't work. It doesn't work. Here you have the comparison with 0 incoming data. Here you have the result with the kinetic simulation, and the Euler scheme gives this bad plateau. But it's quite easy to understand why it doesn't work. Since if you look at the eigenvalues you obtain, eigenvalues for the flux matrix of the Euler system, it means U minus the soon speed and U plus the soon speed. You look at the values of the eigenvalues obtained by the kinetic simulation. You start from a situation you have 2 incoming data. Here this quantity is positive, here this one is positive, and here this one is negative. You start from this situation, but very fast, all the eigenvalues become negative. And it means that everything is going out. then by doing our numerical procedure, we do something which is completely wrong. And this is exactly the same situation on the right boundary, since we start with a situation with two fields going outside, and very fast, all the fields are going outside. Then we do something which is wrong. We prescribe something which has not to be prescribed. Okay, how can we cure this drawback? The strategy is the following. You define now as a reference state the value of the hydrodynamic field in the first cell, the first internal cell of the computational domain. Then U1 gives you the U star. Okay. Now I see the value of the hydrodynamic field in the boundary cell, the cell with index 0, as a fluctuation around this reference state. And now I repeat this construction as before by defining the projection on lambda minus and defining the m plus by solving the half space problem, which actually means using the Maxwell approximation. And then I obtain a system, I compute that, and it gives you the numerical flux I use for the nonlinear Euler system. Now you see why the problem is much more difficult numerically, because now the construction of the system to determine the m plus is given by this minimization problem. It can be recast as solving this kind of linear system, but now the matrices involved in this system and the right-hand side depends on the reference state, and therefore they depend on U1, and it changes at each time step. And at each time step, you should reconstruct the matrices. You should compute plenty of integrals to define the matrices. Okay? But of course, you have a gain in comparison to the computation of the kinetic equation. And not that bad. Here, this is exactly the same simulation as before, with 0 as incoming data. And we cure the problem that you observed before. But the situation is not very interesting, since, as we have seen before, very fast everything is going outside for this specific data. And therefore, we prescribe nothing, actually. Then this is not very interesting. Then here I consider a more relevant situation, which is the problem of evaporation condensation, which has been investigated a lot by the team of Kazuo Aoki. The incoming data is given by a certain Maxwellian with given state rho of the wall, u of the wall, and theta of the wall. Usually this quantity is 0, which in principle differs from the reference state, of course. Therefore, it creates the boundary layer because these quantities are not in equilibrium with what happens inside the domain. And then now there is no reason why everything goes outside. You have a situation where some of the characteristics are going inside, some outside, and there the method works fully. And here this is a comparison for a short time between the kinetic simulation and the hydrodynamic simulation. It's not that bad. I will go back to some point about the comparison between the two in a while. Okay, here this is another boundary data. I just changed the parameters, and we observe more or less the same behavior, and here the same with some discrepancy appearing for the velocity here. Okay. Then in particular, I should say that it supports some strong differences on the pressure. Okay, something which is quite interesting to consider with this kind of method. Of course, I show you here short-time simulation. It means that the perturbation of the equilibrium state coming from the boundary here does not cross all the domain. But the method is able to handle the situation where the wave coming from the boundary, from the left boundary goes to the right, and then the boundary condition plays its role. But it's very difficult to do the same simulation at the kinetic level, because you have to pay too much. Then you can do that, and what it has been observed for on the evaporation condensation problem is that you relax to a constant state for the hydrodynamic level. And this is indeed what you observe. Here you remark that the amplitude of the value for rho, u, and theta are very small, and then you converge to a constant state. The problem is that it's difficult to compare the result with the result obtained by the team of Aoki, because here we are working in dimension 1 for the velocity, while the obtained results in dimension 3 for the velocity. Then for the value of the constant depends on the velocity dimension. Then I cannot compare, I cannot say that my results are the expected one. Okay, just a couple of remarks on the method. The first remark is that the scheme preserves equilibrium. I mean, if the initial data and the boundary data are exactly the same Maxwellian, absolute Maxwellian, then it happens nothing, exactly as expected. The only source of errors is the computation of the integrals that defines the linear system I have to solve, the matrix A star, B, etc. Then if you do that job with enough accuracy, it happens nothing as expected. Okay? Then you preserve equilibrium. The comparison with kinetics should be taken with care for the following reason. What we use actually is just a stupid scheme for the kinetic equation. We split, first we solve the transport part, then the collision part, and that's it. But now, if you want really to compare to the Euler equation, you should pick the mean free path very small. Tau should be very, very small. Otherwise, it would be more relevant to consider Euler, Navier-Stokes equation instead of the Euler equation, since you have diffusive term of order of tau. Okay? And if you want to compare really with Euler, you should use tau very small. If you use tau very small, you have boundary layers of size tau. And therefore, if you want to capture the boundary layers, you should take delta x very small. And if you take delta x very small, due to stability constraints, you should take delta t very small too. And then you have to pay really a lot. Okay, and then it's really difficult to make a fair comparison with the kinetics. And it's difficult to me to understand if the errors observed are due to the error in the numerical simulation for the kinetics or due to a drawback in the method. And to make fair comparison, you should look at the result obtained by Aoki, since they made really strong efforts to have very good kinetic simulation. Okay, just to finish with a word on other numerical solution proposed by Delachery. This is very simple. The definition of the boundary fluxes by Delachery is the following. You take the Hall flux associated to the kinetic data, defined this way, and you take the Hall flux going outside of the Maxwellian defined by the hydrodynamic quantity in the boundary cell. Okay, and that's it. You define exactly the boundary flux by considering these Hall fluxes. Then in the Delachery scheme, this is very natural since he uses kinetic scheme for solving the Euler equation. And it's very natural to use these boundary fluxes, and can be interpreted as an Nyquist-Ocher flux. And I should say it's very simple, and I should confess it works incredibly well. And of course, in the scalar case, this boundary condition is exact, as it has been proved in the paper Alexis. Okay. Okay, let me say a few words about the future about this research. What we can do also here, I just spoke about incoming boundary condition. The boundary condition for the kinetic is something which is given, the given distribution function. But you can work with reflection operator as well. For instance, the one that you described before. You can consider specular reflection or diffusive reflection. The point is that the full specular reflection, it absolutely doesn't work, but the theory of Korongol-Sulem does not apply to specular reflection. It can be expected, actually. Actually, the boundary condition at the fluid level corresponding to the specular reflection would be the wall reflection law, just changing u into minus u and keeping rho and theta. Okay? And the problem is a bit different. And you can consider also reflection operator. You have just to modify a little bit the definition of M+, but it works quite well. The main drawback in what I described before is the Maxwell approximation. It looks really crude, and certainly you make plenty of errors at these levels. a bad way to solve the half space problem. And in particular, you can remark that it does not retain any information from the collision operator. You can take the Boltzmann, Fokker-Planck, what you wish. It doesn't change the definition of M+. And this is absolutely not reasonable. Okay, since of course the half space problem depends on the collision operator. And then better approximation can be obtained. I see at least two ways to do that. There is a method based on Chapin-Zog expansion and duality relation, which is described in a paper by Goltz and Clar, that can be used for that purposes. And also in the PhD of Coron, you have some method based on spectral approximation. Okay, then that could be done to retain more information of the collision operator and then to improve the Maxwell approximation. Of course, another possible improvement comes from the recent progress made on the analysis of the half space problem. Since here, as you have seen, everything is based on the linearized theory. In some sense, I'm inverting two limits. The limit as the mean free path goes to 0 and the limit of the linearization. And this is certainly a drawback of this approach. And maybe something can be extracted from the recent progresses of the analysis to do better things at the numerical level. Then, of course, we have in mind to do a multi-D simulation. And as I said at the beginning, it will be very interesting, instead of considering the boundary problem, to consider the problem of matching fluid and kinetic domains. Okay, then the same work is exactly the same. Once we have understood the machinery, what you have to define, what is coming inside, what is coming outside, we have everything that you need to define a matching condition with exactly the same point of improving the Maxwell approximation. Okay, and it will be exactly the same. And then, of course, we are interested in developing the collaboration with Thales, and we wish to go back to models where you take into account the electric effects and considering model for charged particles. Okay, and I thank you for your attention.
I'm not sure if you said that. Might you get into trouble if a shock goes into the boundary where the say a transonic shock, where the time values it exchanges?
The simulation we did, it works quite well, but maybe we did not investigate all the situation, but it works reasonably well. However, I should say that the de Lachery definition works quite well too.
Well, I mean, I still have this question, which I'm not sure I understand. So if you consider the kinetic model, the thermodynamicity as the boundary conditions.
Sure.
Now, if you have a fluid region in the middle, the solution, the nature of the boundary condition is affected by the solution, which is defined by the boundary condition.
Yeah.
So, with your approach, I mean, you're sure that you have uniqueness and rocks.
Are you kidding?
Okay.
No, for the linearized problem, of course,
Yeah.
that's done. But for the non-linear situation,
I see a little problem. Maybe it's a problem that only exists for the stationary problem, because after all these layers, it's a stationary framework.
Actually, the layer may not exist. It's always a flux. I mean, I don't know for this case, but for the simplified case, the situation, even if, I mean, the way you define your flux, considering a layer, does not correspond to the exact layer that actually you can have. Okay, you can have a situation, your situation, you know, when there was no layer, when you put shock, -1, +1. You say, okay, but this is the flux that I consider. Okay, I consider just the layer which is trivial, which gives me the good flux. But it does not correspond to exactly what you have physically if you do the. But I don't know here if it is. Okay. But I'm still surprised actually that you need the mean problem, I mean, we have to discuss.
Yeah, sure.
It seems that there's.
Oh, but as I said also, okay, maybe it's not necessary for that, but the next objective is to consider the matching condition, and then you need everything. This is really a preliminary step to go forward.
Perhaps I had a second small question. Is in that paper by Ukai,
Yeah.
Then they have a very interesting method to existence for the user problem, the husband's problem, which is a penalization problem. Do you think you can use that in the scheme somehow?
I will tell you in the future.
Automatically select the right conditions.
Now, for the time being, I don't know, since, well, I have to work a little bit on the paper of Ukai and Tishenyu to be able to answer. Certainly, there is a room to do something at the numerical level for
At
that.
numerical level,
Yeah.
I mean, without solving, without even.
Yeah, sure. What you want is really to stay cheap. You don't want to see any kinetic things. Yeah.
Any other questions or comments? Okay, so thank you.